only for serious learners. Let's try to understand some critical details around fine-tuning of LLM and how fine-tuning improves the model performance. Let's see step by step. Here are the topics for the video. Today we are going to understand why to fine-tune the LLM, what is the need of fine-tuning. Then we are going to understand the comparison of full fine-tuning versus partial fine-tuning. Then we are going to understand options to fine-tune your LLM. Then we are going to see one of the fine-tuning technique known as parameter efficient fine-tuning. And there is one sub-technique in that known as LoRA technique. So this technique we are going to understand. And then I am going to do Python demo and show you how parameter efficient fine-tuning works and how it helps you in making your LLMs better for your use. So before moving on, guys, I request you to give me a thumbs up if you like my content, because that is the only motivation for me. And it takes a lot of effort to take time out from the full-time job and create this content. Okay. So your thumbs up and your comments will be really motivating for me. With that said, let's go ahead and try to understand why do we need to fine tune the LLM. So a week back, I created a video on prompt engineering and in context learning. So if you see here, at Unfold Data Science, there is a video in context learning versus prompt engineering. In this video, I have explained you how it is difficult to get the job done from the base LLM, core LLMs, when it comes to business specific needs. I'm not talking about generic task. I'm not talking about asking how far is Delhi from Bangalore. No, I'm asking about business specific tasks. So LLMs in its native form will not be able to help you beyond the extent when you want to ask business specific questions or when you want to use it for your own purposes. For example, a financial institute like a bank may have a different kind of use cases, and it will be very much domain specific use cases. Similarly, a hospital or a healthcare service provider, it can have a different kind of use cases, and it may need LLM to do a different flavor of similar task. So what I'm trying to say here is LLM in its native form is very generic in nature. And if you want to make it something which can be used for business purposes, you have to make it specific. And this journey from generic to specific is basically fine tuning of your LLM. Okay. This is a very simple definition of what is meant by fine tuning LLM. How many ways are there broadly to do the fine tuning of LLM? Two ways at very high level: full fine tuning, and partial fine tuning. Now we are going to understand how full fine tuning is different from partial tuning or partial fine tuning, whatever you call it. And this is an interview question, because this kind of scenario will come into picture when you work in industry. And people will ask you, why did you go for partial training? Why did you go for this approach, that approach? So let's go ahead and try to understand the core differences between full fine-tuned LLMs, okay, full fine tuning when you do, and when you do some other technique that fall in the category of partial fine tuning. I will discuss more about this in a moment. But first try to understand partial fine tuning. What are the how it differs from full fine tuning. The concept is very simple, guys. In full fine tuning, you train all the weights of your model. For example, in your original model, if you take any LLM, for example, GPT-4, right? There will be, let's say, 100 weights, just an example. All these 100 weights will get retrained, relearned, okay, when you do full fine tuning. When you do partial fine tuning, there are different ways in this, but it will not be all the 100 weights most of the time. It will be a subset of that. So it is not like making the model completely from the scratch again, or altering all the weights again. It will be some kind of partial weight updation. Okay. And then we are going to compare how these two things are differ. So first difference that I just explained you, all params, all parameters of your model will get updated here. This I'm talking about full fine tuning. Here only some params will get updated. Only some params updated. End of it, it's a deep learning model. So you can think of a weight matrix, some weight is getting updated. Second, we have to think from the perspective of cost of training. Okay, cost of training. So what do you think it will be here? It's very simple to understand. You are training a big model here. So training cost and training time both will be high here. On the other hand, training cost and training time both will be low here. Fine. The third thing that you need to understand, cost of storage. Cost of storage. Cost of storage also, since you are training here full model, high, and here since you are kind of making it small, so training small things, so cost of storage will be lower, except in some scenarios that is specific that we will discuss in upcoming videos. No problem on that. But normally training, storage, all these costs are high. Okay. Is there an issue of overfitting? Yes. When you do full fine tuning, then there is a quite possibility that your model may be overfitting and your model may not be generic now. So previously your model was generic. This model, when you started, it was generic. But if you do full fine tuning, you are altering all the model parameters. So there is a possibility, high possibility of model being overfit. In this scenario, low possibility of model being overfit and a good possibility that your model is still generic in nature. Then some more things you need to understand here. The size of the model here will be same as the original. Size, I am writing same as original because you are just altering the weights here. But when you do partial fine tuning, the size may not be same. It almost same, but not exactly same. Okay, size almost same because sometimes you add some layers, but not exactly same. Okay, so size will be same as original in terms of how many parameters you are training. I'm talking about here. Okay, and don't confuse with cost of storage here. Cost of storage is basically when you are training the model, how many parameters you are training, how many weights are there, biases are there, all these things will get stored somewhere, right? So here I'm talking about the final model learned weights and biases. Here I'm talking about final model learned weight and biases. Okay, this model is less scalable in nature. Less scalable because you have retrained the entire model, which was previously generic. Now you have made it less generic. But here, since your model has some component of still generic, so it is more scalable. You can use it for multiple purposes still, but this one may not be true. And this one is when to use this. Okay, so if you have a very specific use case, the last point is important. If you have a very specific use case and you don't bother about resources and no worry on resource. If you have these two things, right, very specific use case which can't be fulfilled by a generic model. For example, you would have heard of Bloomberg GPT. Okay, very specific use case can't be fulfilled by a generic model which has learned from the Wikipedia internet page. Then you go for full fine tuning. Most of the cases we go for partial fine tuning because it is resource friendly and it is generic, so it can be scaled, it can be used for multiple purposes. So I'm writing here for multitasking you can use it. Resource friendly and multitask. Now if somebody asks you in interview, how is full fine tuning different from partial fine tuning, you have 6-7 points to talk. Okay, you can talk on these points. Now, from this comparison, you would have understood the core differences is this full fine tuning will be money wise costly and parameter efficient partial fine tuning will be money wise less costly. So any businesses, any companies, they will want to try this first, obviously, because everybody wants to save cost. And if this gets the job done, then everybody is happy. And most of the times this gets the job done. So in partial fine tuning, what are the different ways to fine tune your LLM? I will write here a few things. Don't get overwhelmed by this. Okay. I'm just giving you a high level knowledge on what are the different ways of doing partial fine tuning, not full fine tuning. Okay, full fine tuning is simple. You simply fine tune model with your own data. Okay, one technique in partial fine tuning is known as parameter efficient fine tuning. What is parameter efficient fine tuning? Parameter efficient fine tuning, also standing for PEFT, PEFT. Okay, so every time you hear the word PEFT, you should understand parameter efficient fine tuning. Parameter efficient fine tuning is fine tuning small subset of your model. So suppose your model LLMs are normally huge, right? Out of that huge model, you just train a small subset of the model. You don't train, let's say there are 100 weights in the model, you train 5 weights. Just a loose example, but think like this. You just train a small subset, or you train the last layer of the model, or you train something else from somewhere and paste it on your model. So these are different ways of parameter efficient fine tuning. In parameter efficient fine tuning, there is one technique, lowest rank. A stands for something I'm forgetting now. I'll give you in the comment. And this method, I'm going to show you demo also in Python. This method helps you to do one way of parameter efficient fine tuning. Okay. The second way of doing a partial fine tuning of your model is called feature based fine tuning. Feature based fine tuning. What happens in this fine tuning is you use a pre-trained model as a feature extractor. Okay, and you just fine tune heads. So let's not go into much detail of this, otherwise it will be a lot of information for you unnecessarily, but I'm just trying to tell you a pre-trained model as a feature extractor. Just remember this. Another method that we use in this category is called layer wise fine tuning. Okay, layer wise fine tuning. Again, I'm discussing this because if you go and say Gen AI in interview, they will ask you what are different ways of partial fine tuning. Okay, layer wise fine tuning, fine tune specific layers of your model. Fine. Another fine tuning method is known as knowledge. This I had mentioned in topics to know, actually, in one of the knowledge distillations. Okay, what happens here is transfer knowledge from a large model to a small model. This is again a fine tuning method, but not everything is trained. Then there is something known as meta learning. Okay, you don't need to know everything, but at least you should know at high level what decision what this does. Learn to adapt new task with minimal updates. That is your meta learning. Okay, and the last one is known as selective fine tuning. Selective fine tuning, as you know, this is a consistently changing field. So some people can give you a larger list or a smaller list, but these are the important broader categorization that I feel you should know. So fine tune part of the model based on relevance of tasks. Suppose I want to do a sentiment classification. I do one part, I do other task, I train some other part. So selective fine tuning. Okay. Now let's go ahead and try to understand how LoRA works in parameter efficient fine tuning. As I told you, what happens in PEFT is not all the weights of the model is trained, only a subset of weight is trained. Fine. So I'm going to talk about how LoRA works here, and I'm going to give you some steps here. Okay. First step is you freeze all your original weights. Okay. Freeze all original weights. Fine. Original weights of your LLM is frozen. The second step is ingest to rank decomposition matrix. I'm going to give you one example also. To decomposition matrix. Imagine there are two matrices that come into picture now. Fine. Train the weight of smaller matrix. So these smaller matrix are there. So we will train weight of not the original model, but the smaller metric, this smaller metric that we created in step 2. Fine. And as a last step, what will happen is update original weight. When I say update, you should not think that original weight is getting updated. You should think that this is one additional component that has come into picture. Okay. So update original model. I will do my training with original weights are there, and then these two metrics are there. Once I have these two metrics trained, right, what will happen then? I will have a new data with me. Okay. And that new data plus my old frozen weights, right, that becomes my new model. So the original weights of the model is not going into training. These two new metrics only is going into training. Okay, let's try to understand with an example. So suppose, so there are two-step process here. Step A is how to update the model I'm talking about here. Okay, model original weights has not gone into training, but model needs to be updated, right? Then only we call it a fine-tuned model. So how to update that? Imagine there are two metrics. One matrix is called A, another is called B. Okay, so this is your B metric and this is your A metric. Both are small metric. When I multiply this, I will get a B cross A metric. Okay, after model training. And first is train model on the data, get this B cross A, and the second step, or this should be B. The second step is add to original weight. Add to original weight. Okay, so suppose this is your original weights of the model that was frozen in the beginning. Original weight plus BA, product of BA, right? This entire thing becomes your fine-tuned model. This entire thing becomes your fine-tuned model. Okay, let's take a real world example from the attention paper and try to understand how this will work. So normally transformer weights have dimension of P cross K is equal to 512 into 64. So number of trainable parameters in transformer is this much. Okay, I mean writing here TP. You should understand TP means trainable parameters. This is original transformer. Suppose I use a rank of 8. Now rank is an important concept in the world of LoRA. So rank is basically when you are creating these metrics A and B, how big or how small you want to create it. Okay, so if you say a rank is equal to 8, then A matrix will get created with the size of R into K. That means the size will be 8 into 64, which means the size will be 512 trainable parameters in A. When your B metric is created, the size of B metric will be D into R, which means 512 into 8, which means 4096 trainable parameters. Fine. In total, when you fine tune your model, you will have 4608 trainable parameters when you train your model, fine tune your model. Now imagine if you do a full fine tuning, you will have to train these many parameters. Whereas if you do a LoRA training, you have to train these many parameters. This is a 86% reduction in the trainable parameters. Okay, so if you do a full fine tuning, you need to train all these parameters. If you do a LoRA training, you need to train only these parameters. This is 86% reduction in the how many parameters you want to train. Why rank is important? This rank we have fixed 8. So the way metric A and metric B is getting computed, right? It will depend on this rank. Now rank is again a hyperparameter. We can tune it. when we define LoRA. But to understand, you should understand rank is one parameter that tells you how big or small you want your A and B to become. Fine. Now, by looking at this, what we should understand is at the moment you want to use a parameter efficient fine tuning. You are not doing a full fine tuning. You are doing a partial tuning. In this technique, LoRA, you are taking two metric A and B. You are training those two metric weights. In the end, what you are doing is you are just whatever trained thing you got right, that you are adding to ordinal weight and calling that your fine-tuned model. So what we are achieving out of it? We are achieving out of it 86% reduction in as compared to full fine tuning, which means this will be faster and this will be simpler to do. Okay. With that said, what I'm going to do is I'm going to cover all these in upcoming videos, the different things I wrote here, right? Different ways of fine tuning model. Feature based fine tuning, layer wise fine tuning, knowledge distribution, meta learning, selective fine tuning. All these will be done differently, but today the topic is mostly on PEFT and LoRA. Let's see how it works in real world. Okay. So let me go to my Google Colab here. Let me go to my Google Colab here and I have run this model. I will give you this in Unfold Data Science Generative AI GitHub, but try to understand what is happening here. Before I start this, I want to give a big thank you to one of the Medium article. This is a member only story since I'm a Medium member, so I'm able to read this. So a big thank you to Shaw Talebi. I have taken some reference because I was looking for a good example of LoRA and which should run faster and which should take less data, and many things we need to see, right? Because otherwise it keeps running for hours and hours together. So this is a very nice example that I took and I'm going to show you using that. So first of all, I'm installing dataset, transformer and PEFT. PEFT stands for parameter efficient fine tuning, and then evaluate. Okay, I have run this, so I'm not going to rerun. I've just run like just before starting shooting. Okay. From datasets, load dataset, data dict and dataset. This is basically transformer things for working with data. From transformer, importing auto tokenizer, config. All these are just to create your tokens. Again, if you want to learn about how pipelines tokenizers work, you can search Unfold Data Science Transformer Pipelines in the YouTube. You will get the video. From PEFT, I'm importing PEFT model, PEFT config, get PEFT model, LoRA config. Okay, LoRA is the one we have discussed. PEFT is the category in which LoRA will fall, and then we will define the various parameters. I'm taking evaluate, torch, numpy as NP. I'm taking a data set where I have a sentiment of a given sentence. Basically, I have trained data set of this size, validation of this size, and number of rows of test is this size. Okay. I'm taking a Robota based model, which is good for classification kind of task. And we should define label mapping like this. Otherwise, sometimes the model confuses and it's not good. Auto model for sequence classification. From pre-trained model checkpoint is the name of the model. How many levels we have? What is my ID to level and what is my level to ID mapping that I'm supplying here. So if you see, this is my Robota model. Robota model is basically classification model that will do the classification of a sentence given a sentence. Now I'm creating a tokenizer here from pre-trained model basically, and for the special token, this padding and padding which side truncation should happen and some generic data cleaning stuff here, then tokenizing the sentence, then data collector from the tokenizer. We are taking the accuracy as evaluate.load. And here what I'm doing is I'm just computing the metric to pass to trainer later. Okay. I'm just giving some sentences if you see here, and I want to see the sentiment of these sentences. These are basically movies. So whether it's a good movie or bad movie or what kind of movie. So if you see here, a feel good picture in the best sense of term, resourceful and ingenious entertainment. It's just incredibly dull. The movie's biggest offense in its complete utter lack. So in model in its untrained model prediction. So model in its original form without fine tuning, the actual model I'm using Robota base. Okay. In this model, if you see here, right, A feel good picture in the best scene of term, positive. Resourceful and ingenious entertainment, positive. It's just incredibly dull. This should be negative, but this is positive. The movie's biggest offense is its complete and utter lack of tension. This is also positive, but this should be negative. Impress you with open-ended and surprise. This is positive, fine. Unless you are in dire need of no result to see it, positive. I think this should also be negative, okay? As you can see, the original model is not that great because it may be trained on a generic data set and not good on um, movies and predictions and those kind of things. That is the reason we have downloaded the data here for training purpose. We will go ahead and define a PEFT model. So again, from the theory, we are going to define a LoRA model. And in LoRA model, what are the things we need to have? We need to have a rank. What is rank? Rank is this R. When I'm creating a small metric, what should be the R size for my metric? Come here. If you see PEFT config is equal to LoRA config, task type is equal to sequence classification. Fine. Here my rank is 4. You can make it 8, 16, 32, whatever. Okay. LoRA alpha, LoRA dropout are two hyperparameters. You can tune this. Target modules is query. No problem. In PEFT config, if you see, right, you can see here, this is your configuration that you have passed in your model. So basically rank and some, these are basically, it's a deep learning model. So whatever you want to give it in dropout, alpha, some parameters, hyperparameters, etc. Some hyperparameters basically. Then I'm doing get PEFT model. From the Roberta model and PEFT config, get PEFT model. And then I'm saying print trainable parameters. Trainable parameters in this new model, is basically 665858. Okay. All parameters in actual model is this much. So how much parameter I'm training? Less than 1%. This line is important here. Okay. This line is important here. So if you see here, right, I told you there is 86% reduction is how many parameters as compared to full fine tuning. If I do full fine tuning here, I'll be training these many params, but now I'm training these many only, which is 0.53%. Here I'm giving some epochs and some basic hyperparameters, and then you define your training arguments. Okay. So in training arguments, you give your output directory where you want to store model, learning rate, batch size, number of epochs, weight decay, and all these normal things. And in the trainer, you simply call this Roberta model. Model is equal to Roberta model. Okay. So Roberta model is the model. I think my session disconnected and then some variables are whatever change I made in the end moment, right? This Roberta model, right? This Roberta model is the model that is I'm going to train. Okay. So Roberta model is my model, but I'm just thinking why here it was model. I mean, when I was checking the how many parameters I'm training. Okay, okay. Inside I'm taking Roberta model, so not a problem, not a problem. I was thinking because session got disconnected, so maybe my changes did not save, but that's fine. Inside I'm taking Roberta model, so it is fine. Okay. And here what is happening is I'm just passing Roberta model and training arguments and training validation and data collector and compute metric in one epoch only I'm training. Okay. So if you see the flow here, right? You are simply defining your PEFT config. You are giving your configurations. And then in this one, you are defining your training arguments. And you are simply training and validating. And then you call training that train. I'm running just one epoch. I'm getting 93% accuracy. And if I rerun right, you will see that in the fine-tuned model, all these sentences will start making sense. See, the movies, it's just incredibly dull. This is negative. So in the original, right, incredibly dull was positive. Similarly, the movie's biggest offense in its complete and utter lack of tension. Negative. Initially, it was positive. Okay. And so on and so forth. If you check by giving different sentences and different input, right, you will see that after fine tuning your model has started performing better. In this scenario, you have fine tuned on a classification task by giving classification data as input. So this is the data you have imported here. This is the data you have imported here, and you have trained on this data. What you can do is you can take a different data and compare the performance before and after training. Okay. I'm going to give you this notebook. Take this notebook, try to change the LoRA configurations, the hyperparameters, the things, and see how model is behaving differently. But the idea here was pretty simple to make you understand four things mainly. One is why there is a need of fine tuning. Okay, I can't stress on this enough. There is a need of fine tuning always. Okay, how full fine tuning and partial fine tuning are different. So you saw one example how we are coming to almost 99% effort is gone in partial fine tuning. What are the options? We prepared a list of things, and then understanding Peft and LoRa, and then Python demo. So we understood these things. The Gen AI playlist will continue. I want you to comment me in which area I should create more videos, whether on LLM fine tuning, or I should go in depth into prompt engineering, or I should go in depth into RAG. So from RAG, right, I remember I wanted to show you RAG video as well. So RAG also is one of the technique of making your model useful. So you can go to this RAG video and you can learn about that. And then obviously fine tuning and all these things are there. So with that in mind, I will see you with the next interesting video. Please give me a thumbs up, guys. As I said, that is the only motivation, and just keep dropping your comments, questions, everything. See you all in next video. Wherever you are, stay safe and take care.